Perfect. There we go. All right, guys. So first off, trig parent graphs. Whenever you're solving trig equations, it's kind of good to know how the parent graphs look, because really when you're solving an equation, you're trying to find points of intersection between two expressions. For example, if we're solving this trig equation here, 5 sine x plus 1 equals 3 sine x, those are two different trig functions, and you're looking for where they intersect. Or you can move everything to one side and find x-intercepts. But either way, you kind of want to think of these graphically. That, okay, sine looks like this, cosine looks like this, cosecant looks like this, secant looks like this, tangent looks like this, cotangent looks like this. And there's all these different properties, like, oh, they're even, odd functions, continuous, not continuous, highs, lows, asymptotes, where they increase, where they decrease. This is an incredibly comprehensive cheat sheet for graphs and trig functions, but we're not doing graphs in this unit, right? We didn't do that. You guys did that last semester with Ms. Wong. So, but just good to understand how these look, because this will help in solving these equations, right? That involve trig functions. Okay. And for the most part, we're going to be solving our equations over the set of real numbers. So what we did last time, or the homework here, this was 0 to 2 pi. That was one revolution in the unit circle. We want to actually solve for all real numbers, meaning we need a general solution. So I'm going to show you how to write that in just a little bit. But we're going to be providing general solutions for this stuff. So still using a circle, but then we're going to have to add or subtract multiples of 2 pi. I'll show you how that looks in just a little bit. And of course, I'll use decimals to kind of help you understand why we're doing it this way, because it's good to be able to graph these two. And we're also going to use a letter called k, where k represents an integer next to 2 pi or pi. You'll see why I'm doing that in just a sec. So let's, and we have many examples we got today. Oh, easy, just 4 examples, lovely. And then after that, we'll do the quiz. The quiz, again, I'll show you what's up with that. We'll do a little review before the quiz. And you can use any notes or homework or whatnot. That's totally fine. So it's like a homework quiz, put it that way. So 5 sine x plus 1 equals 3 sine x. Cos x plus 1 equals sine x. Okay, so we have these 2 examples. So here's what I would do. I would actually move this to that side to get this. And then move that 1 to the other side. And then do this. Does that make sense? What I just did? It makes sense? Okay. Now think about unit circle. I'm going to do a makeshift unit circle right here. Where is y going to be negative half on the unit circle? Well, first of all, which quadrants is y negative? Choose 1, 2, 3, or 4, or combination. Which quadrants is y negative? 3 and 4. So I'm going to go, so thank you, Liam. So yeah, 3 and 4. So it's going to be over here and here, where you have root 3 over 2, common negative half, and root 3 over 2, sorry, negative root 3 over 2, common negative half. Okay. And what are the angles that go with them? 11 pi over 6. Is that right? Yeah, and 7 pi over 6. So you have 7 pi over 6. And also you have 11 pi over 6. However, if you're doing this for all real numbers, couldn't we go around the circle once and then stop over here? Right? We could do that. That's possible. Can I go backwards and say that? Sure. And likewise for 7 pi over 6, I can go backwards. And I can go around. And, by the way, I can go around many times and stop over here. Right? There's multiple possibilities. In order to express that, here's what you do. You say this. Plus 2 pi k plus 2 pi k. And you make a statement that k is any integer. Remember, integers are like whole numbers, but they have negatives as well. That's how you state a general solution. So this is what we call all this right here is called a general solution. All that's called a general solution. So yeah, 7 pi over 6, 11 pi over 6. But plus 2 pi k. K could be 1, 2, 3, 4, 5, 6, 7. K could be -1, -2, -3. There's infinite possibilities. And why is infinite possibilities? Because look at the graph of. Let's say I focus on this part, right? After I move everything to one side. Let's say I graph that in Desmos, 2 sine x plus 1. And look at the x-intercepts. Let me clear the screen for a moment. See, -5 pi over 6, -pi over 6, 7 pi over 6, 11 pi over 6, 19 pi over 6, 23 pi over 6, 21 pi over 6, 35 pi over 6. These are all, not multiples, but they're all extra angles, right? As you do more and more rotations, they're all coterminal. That's what I'm going to say, coterminal angles, right? That's why we talk about coterminal angles in the beginning of the trig. All the trig stuff you're doing, like, yeah, here's 11 pi over 6. What's coterminal? What if I go around once? What's that? What's that when I go around once? That's 2 pi, right? Add 2 pi to 11 pi over 6. How would I do that? Well, think about it. 2 pi is 12 pi over 6, right? 23 pi over 6. Look at that, 23 pi over 6. So that's why we have to write it this way, as 2 plus 2 pi k, where k is any integer, so also negatives are taken care of as well if you go backwards. So that's called a general solution. So you really got to read carefully what I'm asking you to do, because if you just put 7 pi over 6 or 11 pi over 6, you're not going to get quite full credit.
So the 2 pi k over 6.
No, just 2 pi k. Just 2 pi k. Because what it means is that you're doing a full revolution, you get back to this place. It guarantees you get back to this location. So it's coterminal angles. You don't have to put plus or minus. I mean, if you wanted to, you could. It's not necessary because k could be negative as well, because we're assuming k is an integer. Okay. Now, this one's a tricky one. And you're given a hint here, square each side. And I'll be honest, I didn't know that was what we had to until I read that hint. So I was a little lost myself. But sure, we'll square both sides. See what happens. Oh boy. Oh, I know. I know what we're gonna do. Okay. Okay. All right. So you guys saw how I got from the second to the third line? What did I do to go from the second to the third line on the left side? FOIL. Yeah, I got FOIL. And I trust you guys with FOIL correct. Don't square them individually. Don't dissipate the order of operations. Don't write cosine squared x plus 1. You gotta do cosine x plus 1 times cosine x plus 1. Otherwise, you're gonna totally mess this up, or you're gonna get so lost. So you gotta make sure you follow all the algebra correctly. Now, this is still confusing because I see a sine and a cosine. I probably want just one trig function, right? It'd be easier if I could substitute for one of these trig functions to make my life easier. But I'm already kind of committed to cosine on the left side because cosine is already pretty involved. So what do I should do on the right side? How would I change this on the right side? You guys remember this? Oh, it was on the board.
Oh, cos 2 theta equals cos squared theta minus.
Not quite, but let's do this. Wait, do you mean this? I'm sorry, I didn't quite follow what you just said. Is that what you said? Okay, we should do that instead. Oh, that may make it more complicated, I think, because now also you got 2x as an angle, right? That makes it kind of more challenging. Let's make it less challenging. So I use the Pythagorean trig identity because that's true. We know this now. So now I combine like terms. Those cancel. Bring that over. I think I'm going to be okay. 2 cosine squared x plus 2 cos x. I can factor out 2 and a cos x. So cos x equals 0. Because if you have 2 cos x factored out, clearly cos x has to be 0 to make this work. Does that make sense? I'm just doing factoring, right? That's all I'm doing. Just doing factoring. And that's at pi over 2 and 3 pi over 2. also cos x could equal -1, right? And where does that happen at? Being pi? Yep. Now here's how you could write your answer though, because it's a general solution plus 2 pi k plus 2 pi k. And clearly don't overthink it. Just put it there. That's it. It's just one, it's like window dressing. It's one little thing you do. That's it. It's no different than what we did last week, or sorry, last class. Just you add a little small wrinkle to it that, oh yeah, it's a general solution. There you go, plus 2 pi k. Pi plus 2 pi k. 3 pi over 2 plus 2 pi k. Pi over 2 plus 2 pi k. Yep. Yep, that's it. Because then it assumes that, okay, we can go around many times. Yep. Yes, there is some unit circle. Totally. There's some unit circle that's happening here.
Yeah, we just have to add the plus 2 pi k.
General. Yeah, just asking for this. That's the only small wrinkle. If you see this, you plus 2 pi k. This is 0 to 2 pi, then you go from 0 to 2 pi. Now, if I wouldn't do this to you guys, but well, the Niners lose might be a little scratching there. I already wrote the test, but sometimes some people could just do like really wacky intervals, like, oh, let's solve from like 4 pi to 6 pi, and that would be a little more complicated. Then you have to kind of go around a few times, but that's all right. I'll be a grunt out if the Niners lose, so I think they'll win though. All right. There's been too much heartbreak. They have to win. They have to get it done this year. I think we're fine. We can just give the ball to McCaffrey. McCaffrey can't get hurt. Knock on wood. All right. Okay, let's move on to example 3, guys. All right, so same thing. And just to keep this kind of tame for you guys, we won't throw tangent into the mix with this kind of stuff, because that's a little bit more complicated when tangents involved with these kind of problems. A simple tangent I can give you from last class, but for this particular lesson, I think we'll avoid that. So yeah, let's work this out. Cos x minus 1 equals sine x squared. I'll leave the left side alone, and then I'll change this to 1 minus cosine squared x. So then you get cosine squared x plus cos x minus 2 equals 0. So I treat it like a quadratic. Move the cosine squared x from right to left, move the 1 from right to left, and then treat it like a quadratic. And if you factor it, you should get cos x plus 2, cos x minus 1. So cos x equals -2, or cos x equals +1. I think I did that right. Yep. Cool. Well, x, forget about this one. That can't happen. Cosine x can't equal -2. But that happens at 0 or 2 pi and so forth. But you can write it like this, though. 0 plus 2 pi k. But if you think about it, 0 plus anything is just the thing, right? You just write 2 pi k. No, because that's not what x equaled. Cosine x equaled that. That's what x equals. Yeah, 2 pi k. That's good enough. Like 4 pi, 6 pi, 8 pi, 10 pi, any even number of pi, any even multiple of pi would work. And again, you should say k is any integer. You should say that. So k is any integer. All right, questions? All right, one more. Let's do one more. I would actually divide everything by 2 first to make your life a little easier. Factor, right? Easy peasy. So cosine x equals 3. Well, no, that can't happen. Or cosine x equals -1. Where's that happen, guys? Where's cosine -1? pi and plus 2 pi k. Because it can go around many times. If you think about it, it's every odd multiple, but just write like that. Just keep it simple. K is an integer, so. Let me make sure the homework doesn't have anything wacky, because I'm surprised that, because I want to make sure there's not a tangent in the homework, because then that would be tough for you guys. Well, she did do that. Well, I'll let you guys battle with it. Okay, well, there's not many tangents. Okay, that's good. It's only one or two. Or there's one verified. Okay. So homework will be 1 through 11 all. All right, posted to School G, the assignment. Okay, for the quiz today. So first off, let me give you guys the review packet before I forget. You don't have to start this today. Wait till Friday to start this, because there is homework for 5, 6 to practice. But if you really want to get started, scan. And by the way, it's 3 questions. The answers are really good. Let's have it here. We will take that. Let's see if it actually does all this. Work. Same deal all the time. Okay, really quickly for the quiz today. On this review packet, I'm going to be asking 2 questions on the quiz today. One question is like number 15. Just like number 15, I'll give you some trig function, do what quadrants in, draw the triangle in the right place, and then use, and I'll give you the formula, like sine 2a is 2 sine cos. It's on the board here too. One question like that.
Wait, sorry, what did you just say?
No worries, I'll say it again. It's all good. There'll be a question like number 15 on the quiz today. Something like that we did last class, or sorry, last week. And it's something like 11, something like that one. That's a quiz. And feel free, this is like a homework quiz, right? So feel free to use your homework or notes, whatever you want. Any resources, totally fine. And you don't need a calculator either. Blank unit circle, I'll give you guys one. Need it?
Willie.
Yeah, I'm just saying a homework quiz, so
What are you talking about?
yeah, that's what I'm treating it. So. Yeah, if you want, you don't actually want to. But so want to, that's fine. You don't have to. Yeah, well, that room's locked. I mean, I think someone used it, so.
Like, please don't check on that sheet or just it's on the words.
I just wanted to on it anyway.
Oh,
Yeah, yeah, hold on.
okay. Thank you.
Oh, they're even blank news for person.
No, oh, wait,
All right, once you're done, just bring it up to me. Then you guys can start homework. And then, of course, if you get the homework done, you could do the review guide as well. Yes, give me a sec. I'll come chat with you. Just make sure my ducks over here. Next week, no.